So, welcome everybody. I first want to thank Carla, Andrew, and Bridget for putting together this wonderful program, but also for the very clear and elaborate instructions on how to deal with this novel format and the discussion rooms and all this. So it really worked perfectly until I started trying to share my screen. So this is a methodology session, and I will talk about time-dependent density functional theory. In particular, the calculation of the real-time spin dynamics. The motivation for this it's not forwarding. Something is wrong. Here we go. So the motivation is to make memory devices and storage devices faster. Typical magnetic random access memory, as well as the magnetic hard drives, work on a time scale of around 1 nanosecond per bit. As you know, in recent years, these magnetic devices have largely been replaced by so-called solid-state drives, SSDs, that do not work with magnetism, but they are of a similar speed. So it's again around nanoseconds per bit. And the crucial question is, can we make this somehow faster? I will try to answer this question, and indeed we can even go down to attosecond processes with the switching of magnetization, as I will demonstrate. My talk has 3 distinct topics. First is laser-induced demagnetization. This is more like an old topic. This was found experimentally in 1996, and I would claim it is now fully understood with TD-DFT calculations. An important aspect there, as I will show, is time-dependent spin-orbit coupling. Then a very different topic is a process that we termed Oyster, the optically induced spin transfer. It works on a much faster time scale, so laser-induced demagnetization works on a time scale of 50 femtoseconds. This process, Oyster, works an order of magnitude faster. It seems to me popular in this field of physics to name effects after animals like rabbit or spider. So we have added an oyster to this here. It was an effect that was predicted with TD-DFT in 2016 and found experimentally 2 years later. First by the Eschliman group in Kaiserslautern, and then by several other groups as well. So that's the second topic. And the third topic will be, since this is a methodology section, an important aspect of what a good exchange correlation functional is for this kind of non-collinear magnetic effects. So this first topic, laser-induced demagnetization, started with this experiment here. It's in 1996 by the group of Bigot and Beaurepaire. And what you see here is that as a function of time, the magnetization, this experiment was for nickel, bulk nickel, goes down significantly. It's what you see here on the time scale of about 1 picosecond. Now, by now, one knows that one can do this even much faster, of a time scale of, let's say, something like 50 femtosecond. But if you think about it, this is quite surprising, because with the intensities that were used, the laser does not act directly on the spin, right? So the magnetic component of the laser is very small. So there's no direct interaction with the spin. So how can this be that this happens so fast? And there have been many propositions in the laser. First was a study that actually investigated the importance of the magnetic component. Then another proposition was spin flip electron phonon scattering. And finally, spin transport, where the idea is that in the interesting region where the laser focus is, there's initially some magnetization which then moves elsewhere in the material so that the magnetization inside the laser spot goes down. So all these three effects exist, there's no question, but it turns out if you look at it within ab initio calculations, the first one and the second one are too slow. They don't account for this very fast demagnetization. This effect is there, and it's an important aspect, but what we found, it's only half of the story. There's another half which has to do with spin orbit driven spin flips that I will discuss in the following. Okay, now when we talk about magnetism, the quantity of prime interest, the object that you want to calculate ultimately, is the observable that is called the spin magnetization density. It's a vector field. So think about it. If you have an electron that moves throughout otherwise empty space, then one can say, well, this electron has a spin and it has a charge. But then in a solid or in an atom or a molecule, then we have a wave function. So it's not really a good idea to talk about the spin, right? What, like for the charge, like there's a distribution of the charge, and likewise there is a distribution of spins, and that's exactly this object here, spin magnetization. So here's an example that's a chromium monolayer. I will come back to this later. And the way I present this throughout the talk is with a color coding for the absolute value of this vector field. So this guy is plotted here, the absolute value. And these little arrows, the little white arrows, they all have the same length, and they just indicate the direction of this vector field. So this is the quantity we want to calculate. And the theoretical approach is real-time TDDFT. Here's the equation. So it's a weakly relativistic generalization, one could say, of the original Longer-Gross equations. So let me discuss the terms here. This is the time-dependent Cohen-Sham potential. It's a scalar potential. And this object also appears in this time-dependent spin-orbit coupling term. So it's really something else than the usual spin-orbit coupling. Usual spin-orbit coupling is time-independent. It's just the nuclear potential. This is the time-dependent Cohen-Sham potential that appears here in the standard spin-orbit coupling expression. Then furthermore, there is a Zeeman term here involving a Cohen-Sham magnetic field. And these two quantities, the Cohen-Sham potential and the Cohen-Sham magnetic field, are given by the standard expression, external potential given by the lattice, Hartree term, and an exchange correlation potential. And in the absence of external magnetic fields, the Cohen-Sham magnetic field is just given by the exchange correlation part. And it's these two objects, the exchange correlation potential and the exchange correlation magnetic field, that are universal functionals of the density and the magnetization density. So as you can see here, the vector of Pauli matrices appears here. So the eigenfunctions, or in the static case, eigenfunctions in the time propagation time-dependent orbitals, are Pauli spinors, so two-component objects. And finally, the laser field is given by this time-dependent vector potential. So once you have these Pauli spinors, the density and the magnetization density are calculated from these standard formulas. Now, since this is a methodology section, I will talk about a couple of aspects of the implementation. What we want to describe is cases where the wavelength of the laser is in the visible regime, which means that the wavelength is very large compared to the unit cell. So it should be a good approximation to do the dipole approximation, which means that the electric field of the laser is assumed to be spatially constant, which means that the vector potential that I showed you in the equation is purely time dependent. So this is numerically extremely important, because if it's purely time dependent, the spatial periodicity of the Cohen-Sham Hamiltonian for a periodic solid is preserved, which means that we can implement these equations more or less straightforwardly in a band structure code. And this is done here in the ELK code. It's an LAPW code. And so the people who are the main developers of this code are Kay Dewhurst and Sangeeta Sharma. The acronym ELK stands for electrons in K-space, or some people say, since the main developer is Kay Dewhurst, that it's actually electrons in K's space. And so these two people managed to make this band structure code time dependent. So here's now first result, calculation for iron, cobalt, and nickel bulk. In the first line, you see the laser field. So it's a pulse of about 6 femtoseconds or so. And this is then the magnetic moment. So it's the magnetization density integrated over the unit cell as a function of time for iron, cobalt, and nickel. And you see, indeed, it goes down. So it's normalized here to the initial magnetization. And what is interesting is that during the laser field is on, not so much happens a little bit here, but the main effect actually happens after the laser field is switched off. Now, let's analyze these results a little bit. And one nice thing in these ab initio calculations is, as opposed to experiment, is that we can actually switch off certain terms. And in this calculation here, we have switched off spin-orbit coupling. So if you look at the spin density, there's wild commotion, right? But as you integrate it to calculate the total moment, it stays put. It stays at this initial value, no time dependence. You see that you see nothing. So can we understand this? And there is in fact an exact equation of motion for the spin magnetization. I've written it down here for the Z component. And it has 3 terms on the right-hand side. So this is divergence of the spin current tensor given by this expression. So if we had only this term, then it would mean that the Z component of the global magnetization would be conserved. This wouldn't be a continuity equation. But there's other terms, so it's not conserved. And the first term is what is called the local spin torque. You see immediately it's the Z component of a cross product, M cross BXC. And the second term you can see immediately from the 1 over C squared here comes from spin orbit coupling. Now, if we integrate this equation, both sides, on the left-hand side, then we get the time derivative of the global moment. And on the right-hand side, we get the integral of the spin torque. We get then the global torque exerted by the exchange correlation magnetic field. And there's a rigorous theorem, it's the zero torque theorem, saying that this integral has to be zero. One can prove it mathematically, but it's physically totally plausible. Exchange and correlation comes from the internal forces, from the Coulomb interaction. So the internal forces cannot exert the global torque on the whole system. So this has to be zero. It's perfectly plausible. This term is zero, it's continuity. So the only term that can actually change the global magnetization is spin-orbit coupling. So in this last calculation, we have put spin-orbit coupling equal to zero, and hence there is no change, right? That was the calculation. So it's perfectly clear. Now let's investigate this a little bit further. So what I showed was the global moment of the Z component, because initially these three materials, iron, cobalt, nickel, are collinear. So what could be, in principle, especially if you think of things like magnons, is that the initial Z component would have kind of been transferred to an X and Y component so that the Z component changes, but this is not the case. So as you can see here, the X and Y components stay throughout the propagation very small. And now this is the main interpretive transparency here. We have now decomposed the total magnetization that goes down here. That's the same as what we saw before, into a part that I call excited. So that's electrons that have been excited by the laser pulse. So they are not near the atom anymore, near the atomic centers, but they have been moved elsewhere in higher bands in the interstitials. And their magnetization goes up, while the magnetization of the electrons that have stayed near the atomic centers goes down. And the sum of the two is the total curve that we saw before. Now, the fact, so this is what happens. One could say, well, it's kind of an optical excitation. The electrons that are excited elsewhere in space take spin with themselves. So near the atoms, the magnetization is reduced. Now, the interesting thing is that after the pulse is switched off, this part stays largely constant, changes slightly still, but the global magnetization basically follows the reduction of the magnetization of the remaining electrons, right, near the nucleus. So this is a universal feature that we found in all calculations. And it's also very plausible because I emphasized before that the main cause of change of the magnetization is spin-orbit coupling. And spin-orbit coupling is, of course, much larger near the nucleus because the potential is larger. So this is the effect of spin-orbit coupling. So this is summarized, this finding here. So initially, the laser moves magnetization from the atomic centers elsewhere, and then spin-orbit coupling drives the demagnetization of the more localized electrons. So we can play a little bit with the intensity and the pulse duration here. So you see that a similar decrease in magnetization that you see in blue here, that can be achieved with a high intensity short pulse, can be achieved the same reduction ultimately also with a longer pulse that is weaker. So what counts in the end, what this shows is that the relevant quantity is the fluence. Now what I showed so far is 3D bulk. Now let's look at other systems. And here's again our chromium monolayer. Right, so here are the chromium atoms, right? And the color, remember, is the absolute value of the magnetization. And now let's propagate with the laser. So here's the electric field. And here's a time counter. And what you see here is the main thing, apart from this wild commotion, that you see is that you have a strong reduction of the magnetization near the nucleus, right? The initial picture was this, right? Strong magnetization here near the nuclei, and at the end, it was reduced strongly to a much lower value. So this tells you that this demagnetization is a local process, right? It happens near the nuclei. And this also means that it really doesn't matter what system you're looking at. If this is a chromium cluster, right, you will find exactly the same thing. And indeed, there were calculations by the group of Stefano Sanvito in Dublin who found exactly the same effect for magnetic clusters. So now another calculation for a nickel slab. There you see that this demagnetization is more strong in the slab than in the bulk. And this was with a realistic experimental laser pulse, and this effect was also found experimentally. This is now a comparison with the other mechanism that was proposed in the literature before, namely if you have such a slab here of nickel, which initially is magnetic, and aluminum, which initially is non-magnetic, then upon the laser pulse, you see two effects. On one hand, the reduction of magnetization due to spin-orbit coupling that I just showed you, but there's also magnetization flowing away from the nickel part into the aluminum. So it goes away from one part of the system to another. And so this is, as you see, the magnetization nickel goes down as a function of time, and in aluminum it goes up, right? This is what you see here. It's a relatively long pulse of 50 femtoseconds. And if you then compare calculation with and without spin-orbit coupling, you see that without spin-orbit coupling, so only this transport mechanism, leads to a change of magnetization of 25%, while with spin-orbit coupling, you get 40%. So these two effects are about of equal importance. Okay, so here's a paper that I want to mention that was a collaboration with the Bigot group, where this relative importance of spin transport and spin-orbit coupling induced spin flips was also confirmed experimentally. And the whole thing is also in a very recent review article, just appeared a couple of months ago here, together with the Sanvito group, where these calculations for magnetic clusters are also contained. Now, second topic, very different. It's the Oyster Effect. So we did a calculation on a different material, otherwise pretty much the same kind of TD-DFT time propagation. This was for a material that is so-called Heusler compound, nickel, manganese, antimony. And here, so this was very short laser pulse of 2.5 femtoseconds. Here are the laser parameters. And what we see is a very fast decrease of the magnetization on the nickel atoms, and at the same time, an increase of the manganese atoms, sorry. So manganese goes down, and at the same time, an increase on nickel. What you also see, there's a slight increase of magnetization on antimony, and the magenta curve here is the delocalized electrons that cannot easily be assigned assigned to one of the three atoms. This is interstitial regions where the electrons can also go. So this is what we found. And this is incredibly fast, right? It's 3 femtoseconds where this process happens. And imagine you could make magnetic devices with switching times of 3 femtoseconds. This would be a gain of 6 orders of magnitude in speed. So this would be fantastic. I mean, we don't have a device yet. This is not my job. But this was the prediction of TDDFT. So can we understand this? And the first line here of this transparency is still calculation, and the 2 other lines are interpretation. So what you see here in the first line is, as a function of time, integrated spin density, so the number of spins, if you wish, on manganese and nickel, and delocalized as it changes in time. So you basically, that's the meaning of this plot, is you increase the number of spin down electrons by 1 on manganese, and you decrease it by a little bit less than 1 on nickel. For upspins, you have a large contribution of delocalized electrons. Nickel happens nothing, but you decrease the number of electrons on manganese by 1. Okay, so in the very simplified picture that is depicted down here, you see exactly that. So this is the initial configuration of nickel. So there's very little magnetization, it's been saturated. And then with the laser, you induce a transition from nickel to manganese of a downspin. And you also induce on manganese, where the main magnetization initially is, of an upspin to the interstitial region. So if you then look at the magnetization of manganese before and after the laser pulse, you see initially this is 4 spins up, 1 down. So this is effectively magnetization of 3 spins up, while after the laser you have 3 up and 2 down, so effectively it's 1 spin up. And this is exactly what you saw in this plot here, the strong decrease of the manganese magnetization, right? So when does this happen, or why does this happen? And here is very useful to look at the density of states that is present in the initial ground state. And this is plotted here. So this is upspins. That's the occupied upspins and downspins, and that's the unoccupied upspins and downspins. And what you see immediately here is that there's no empty states available. So the upspins can at best go to the interstitials, to somewhere else. And that's exactly what happens here, right? That's what we saw here. While the downspins, there is empty states, but the empty states are on the other type of atoms. So you have a downspin occupied here. Blue is nickel, on nickel, but available empty states are only on manganese. And it's important to realize at this kind of intensity that we have, the laser does not flip the spin, right? The magnetic component is small. So you have to go from a downspin orbital to another downspin orbital. And the only available downspin orbitals are on manganese. So what you do in an optical excitation, you actually move the electron, including its spin, its downspin, from the nickel sublattice to the manganese sublattice. So from one region in space to another region in space. So you change the local magnetization. You don't change the global magnetization, but locally you change it. That's the Oyster effect. It's also clear that this cannot always happen. So this is what I depicted here. This is what we saw before, nickel, manganese, antimony. But then it depends on what kind of states are available. So this is for another material, cobalt-2 manganese silicon. And here you see the available states at a certain frequency are actually on the same atom. So in this frequency regime, you go from, in this case, cobalt to cobalt, and this effect, Oyster, does not happen. It's immediately clear. Right? And then there's more complicated cases where both the downspin electrons can move from one atom to another and the upspin electrons can move. This is for a compound manganese-3 gallium. This is especially tricky. This is a ferri magnet.
Hardy, sorry to interrupt.
Almost done, almost done. 1 minute. Where you have a ferromagnetic, so this opposite spin arrangement of the spins, but they don't compensate, so it's not an anti-ferromagnet, but it's a ferromagnet. And then if you put all these picture together that I showed you here on the lower plot where the spins go, you see that you have here for this material a ferri to ferro transition within a few femtoseconds. Now, as I said before, this Oyster effect was first predicted by TDDFT in 2016. In fact, these examples that I showed you were from the paper of 2016. And then later it was found, confirmed experimentally by several groups. This is one of the papers of the Ashleyman group, and I just want to highlight here. So they do it even faster, right? So in sub femtosecond regime, and they call it the birth of the research area of attomagnetism. Right? But it's exactly the same mechanism as you see here, right? The transfer of spins from one to another sublattice. This is for nickel-iron alloy. Okay, so I will not talk about the functionals. This is a different topic. I just want to summarize here. So I showed you two effects: demagnetization within something like 50 femtoseconds, which is a spin orbit driven and spin current effect. You don't change the components much of the non-collinear magnetization. What we found is that interfaces and layers have equally importance in the spin current and spin orbit coupling effect. And finally, I demonstrated this new effect that we called Oyster. And I did not talk about the last topic, the non-collinear exchange correlation functionality. Thank you for your attention.
Yeah, thank you, Hardy. We have one question by Daria Gorelova. Please ask your question.
Hello, can you hear me?
Yes.
Yes, I can
Yeah,
hear
great.
you.
So yes, so thank you. So unfortunately, I cannot turn on my video. So thank you for your great talk. It was really great, and it brought me to the time of my PhD when in 2013 finished that I was also doing on theoretical ultrafast magnetization dynamics. So could you please come back to your slide for the first part of your talk where you have shown the equation for the time-dependent equation for equation of motion for magnetic component, and then you have the effect of the spin orbit coupling?
Yes.
So maybe could you speak a bit more about kind of intuitive explanation for that? So of course we can see the equations and understand that if you switch off this term, so there's no spin flip, but could you speak a bit more? How do you see it? How do you understand that?
Okay, so I talk about this, the integrated version. The other equation was just without the integral over the unit cell. So there's three terms here. If the Z component of the magnetization, this is what we are looking at here, the time evolution of the Z component of the global magnetization. If this was conserved, which it is not, but if it was conserved, then we would have only this term and this term, which is a continuity equation.
Mm-hmm. Yeah,
there are terms that in fact change the magnetization, or that can change the magnetization. Now, here's this term, which is the curl of M cross BXC, which is the cross product, sorry, of M with BXC, M cross BXC. And if you had, in addition, an external magnetic field, right? So B external cross magnetization, this would exert a global torque on the magnetization of the system. So you would change, you would cant the global magnetization. But the internal forces cannot do this. So that's why this term is zero. Now, this is spin-orbit coupling. It changes the direction in a complicated way. One thing that you can actually also prove, which is complicated, but you can prove it from the equation, is that initially, at the initial point in time, after you, at the time you switch on the laser, so at the initial ground state, the first moments, this leads always to a decrease of the magnetization. What happens later, we don't know, all kinds of things can happen, but initially you always decrease. That follows from this term here. That's another interesting aspect.